Hi everyone, I'm Sam from Intelligent Visual Interfaces Lab from Rutgers University. I'm presenting our paper, the IVI Lab entry to the GENEA Challenge 2022, a Tacotron2 based method for code speech gesture generation with locality-constraint attention mechanism. We see this gesture generation problem as a sequence-to-sequence mapping with text, audio, and speaker identity as the input and the joint representations as the output. Tacotron2 is designed for speech synthesis, text-to-speech conversion. Later, it's used in voice transformation tasks. The input is a character or phoneme sequence, and the output is a sequence of Miles spectrogram. It has the encoder-decoder architecture and the attention mechanism. The picture shows the architecture of Tacotron2. The image shows our model architecture after we did optimization and modification onto Tacotron2. We define H as the output of the encoder, where T is the length of the input sequence. The attention context model will calculate weight alpha at the S decoding time step using the output of the attention STM at previous time step as I-1. The attention vector GI is calculated by the linear combination of the attention weights alpha I and H. The vector is then used in the attention LSTM and the decoder LSTM. We added the locality constraint to the attention context because we want the decoder to learn the gesture speech alignment from local audio features. The temporal correlation between gesture and speech is strong within a window of -1 in 1 second. We achieved it by adding a mask ICMI centered as the ICE decoding frame as an input to the attention context module. The resulting weight alpha I still sums up to 1, while the value is 0 at the time step where it's masked. In practice, we use the left and the right 3 frames, which is 1 second, as the local window for attention. We think it would be beneficial for the model to strengthen the local audio motion dependency. We define our loss function as shown in the slide, where y is the ground truth, y hat is the predicted sequence by the model, and the y hat deck is the output sequence after the decoder. For optimizing the upper body gestures, we add a velocity constraint. The final loss function becomes is shown on the slide, where the symbol delta means the motion velocity. For the full body gestures, the motion representation includes root positions. The range of the root position is greater than the range of the other drawing representations, so we add a coefficient lambda to its loss component. We use 0.01 for lambda for our FSH entry. As for data processing, we use all the 3 features of audio, that's Miles spectrograms, MFCCs, and prosodies, to train our model. All of them are extracted at window length of 4096 and help length of 1470 under the sample range of 44.1 kHz. The resulting audio features are 30 frames per second with the same sequence length as the motions. We use the Librosa package for the first 2 features. We set the number of filter banks to 64 for male spectrograms and use 40 dimensions for MFCCs. The processes are extracted using the parcel mouse package. All audio features are normalized and concatenated before being passed to the model, and the processes we extracted are audio intensity, pitch, and their derivatives. We use fast text word embeddings with 3 dimensions for processing the text features. We leave all zeros for out of vocabulary words. We add 2 additional dimensions to the text features, one labeling whether the corresponding audio frame is silent and the other telling if any laughter is present. We concatenated the audio and the text features by aligning them frame by frame. The timing of a word is matched to its corresponding audio frame. We observe that there may be more than one word in each time slot, so we evenly divide the duration of their cases. We also added 1 hot vectors for the 17 speakers. We use the exponential map as our motion representation. For the upper body, we selected 19 joints. We add 6 lower body joints and root positions for the full body. The joint names are listed in the table. The finger motions are excluded because the finger data is not as accurate as other joints. Finally, the upper body pose has 57 dimensions, and the full body has 78 dimensions. For post-processing, we smooth the generated gestures using the Swarovski-Golay filter with a window length of 9 and a polynomial order of 3. We find the smoothing parameters filter out the jittering artifacts and preserve better motion quality. As a result, our FSH entry and USK entry both generate fair motion quality in human likeness. However, there's a gap in human likeness between our entry and the natural motion. We think one major reason is that our system does not include finger motions, which limits the upper bound of the human likeness score of our method that can receive. The second limitation, we believe, comes from the stability of our model-generated gestures. Temporal smoothing must be applied after the model prediction. Therefore, the human likeness score will discount by this smoothing. For appropriateness, our full body entry receives the highest appropriateness score among all submitted systems, only second to natural motion. We found our motion responds well, whether it's silent or when speaker speaks, but there's a gap between the natural motion and our motion. We think the higher appropriateness score could possibly come from the design of the locality-constraint mechanism, as the decoder is forced to consider its neighboring 1-second window of features for gesture generation. The second reason may be the usage of all the input features, including the male spectrogram, MFCC, prosody, and laughter. These multimodal inputs provide a lot of information for the model to learn to properly align speech with gestures, as our predicted gestures are pretty responsive to when the speaking starts and pauses. We hope our attempts to strengthening the local speech gesture correlations in the architecture and the gestures generated by our system entries could facilitate further research on gesture generation in speech appropriateness. Thank you for your time.